Welcome to Section 2.3 Sources of Bias and Fairness Basics. Bias in AI systems isn't just a technical issue, it's a societal one. The way data is collected, labeled, and applied directly shapes who benefits from AI and who may be disadvantaged. By the end of this lesson, you'll be able to identify major sources of bias in AI datasets and models, explain conceptual fairness metrics like demographic parity and equalized odds, recognize the trade offs between fairness, accuracy, and subgroup performance, connect these ideas to real world consequences, and describe why fairness is context dependent and why no single definition of or metric can cover all situations. So bias rarely appears as a single mistake. It creeps in through many points in the AI pipeline. It might start with the way data is collected, the way labels are assigned, or the way variables represent underlying concepts. Each of these can distort outcomes and reinforce inequality if not carefully managed. For example, a training dataset may underrepresent certain groups, or a labeler may apply subjective judgments unevenly. In this lesson, we'll explore four major sources of bias: sampling, label, measurement, and proxy bias, and see how each can undermine both accuracy and fairness in real world systems. So, sampling bias occurs when the data set used for training doesn't represent the broader population the model will serve. A classic example comes from clinical trials. Historically, medical studies have often focused on younger, healthier men. Models built on that data may perform poorly for women, older adults, or those with different health backgrounds. The issue isn't that the algorithm is inherently flawed, it's that the sample is incomplete. This mismatch can have life or death consequences, from misdiagnosis to ineffective treatments. Avoiding sampling bias means deliberately designing datasets that reflect the diversity of the real world population the model will encounter. Label bias arises when human judgments used to train a system reflect inconsistencies or hidden assumptions. Even with strong labeling guidelines, annotators can disagree, especially on subjective tasks. One person may classify a sarcastic review as negative, while another sees it as neutral. These disagreements aren't random. They often reveal cultural differences, unconscious biases, or unclear definitions. If such inconsistencies go unchecked, the model learns those same biases. Clear instructions, consensus mechanisms, and diverse labeling teams can reduce this risk. Label bias reminds us all that models are only as objective as the humans who teach them. Measurement bias happens when the tools or metrics used to collect data systematically distort reality. This is especially dangerous because it hides behind numbers that seem objective. For example, fitness trackers often miscount steps for people who use wheelchairs or who walk with irregular gaits. The device was designed for a typical walking pattern, so its measurements fail for anyone outside that norm. When such biased data is used to train a model, the errors get treated as if they were truth. The result is unfair outcomes that appear objective. Fair AI requires questioning not just the data itself, but also how that data was measured. Proxy bias arises when seemingly neutral variables act as stand-ins for sensitive attributes. Even if race, gender, or income are removed from a dataset, other features may correlate strongly enough to reintroduce them. A classic case is zip code. Because neighborhoods often reflect racial and socioeconomic patterns, a hiring or lending model that uses location data may unintentionally discriminate. The troubling part is that proxies aren't always obvious. You may not know a column encodes sensitive traits until the model reveals disparities. Avoiding proxy bias requires careful analysis of correlations and rigorous fairness testing beyond just removing direct identifiers. To respond to bias, researchers created fairness metrics, tools to quantify whether models treat groups equally. These metrics don't fix bias by themselves, but they highlight disparities so they can be addressed. The challenge is that fairness has no single definition. What seems fair in a hiring system may differ from what's fair in healthcare. For example, equal outcomes across groups may be one measure, while equal error rates may be another. Each metric embodies different values. This means fairness is context dependent. Choosing a metric is not just a technical choice, but an ethical and practical decision. Demographic parity is a fairness metric that asks, are outcomes distributed equally across groups? For example, if men and women apply for loans, demographic parity requires that approval rates be equal regardless of group. This metric emphasizes representation and prevents systematic exclusion. But it has limitations. It doesn't account for whether decisions are accurate or whether they are balanced. A system could meet demographic parity while still misclassifying individuals within each group. It's best understood as one fairness lens among many, not a final answer, but a starting point to ensure outcomes don't systematically disadvantage one population. Equalized odds is another fairness metric, but instead of focusing on outcomes, it focuses on errors. Specifically, it requires that false positives and false negatives occur at similar rates across groups. Imagine an AI diagnosing a disease. If one group is overdiagnosed while another is underdiagnosed, that system fails equalized odds. This metric emphasizes fairness in accuracy, ensuring no group bears disproportionate risks of mistakes. However, it can be difficult to achieve alongside demographic parity since equalizing errors may shift overall outcomes. Equalized odds reminds us that fairness often involves balancing competing definitions. Fairness in AI isn't a single switch to flip. It's a set of trade-offs. Improving fairness for one subgroup may lower overall accuracy or create new imbalances for another. For instance, achieving demographic parity could reduce performance in smaller groups, while equalized odds might require lowering utility for the majority. These tensions don't mean fairness is impossible, but they highlight that context matters. The right balance depends on the stakes, domain, and ethical priorities. Fairness is less about perfect solutions and more about transparent choices that reflect values and minimize harm across populations. All right, so in this section, we explored the many ways bias can shape AI systems and the tools used to evaluate fairness. We looked at four sources of bias: sampling, label, measurement, and proxy bias, each capable of undermining accuracy and trust. We introduced fairness metrics like demographic parity and equalized odds, showing how they define fairness differently. We also discussed the inevitable trade-offs, balancing fairness against utility and across different subgroups. The key takeaway is that fairness is context dependent. No single metric solves every problem. And now up next, we'll examine how to detect and mitigate these biases in practice. See you in the next lesson.